the action L as 1/2 e to the power minus 1 okay, if I write x dot square, it means x mu x mu. Okay, so mu is repeated. I can use x mu dot x mu and x dot square. Okay, by dropping the index.
So there should also be dots on the right hand side, right?
Oh, this is actually it has no
No, I
meaning.
mean x dot mu times x dot mu.
Ah, okay. This, I'm sorry. You are right.
Like
You are right, Sarah. This is just x square. I'm sorry. So if I have x dot square, then that would be x mu dot. But if I like, I can also write it as x mu dot. It doesn't. Okay. Is that okay? So that was a crucial correction. Thank you so much. Yes. So I write x dot square minus m square. So what one has done here, one has introduced an extra additional field which is e of tau. So this is also a function of tau. X mu is also a function of tau. So both are fields on the word line. And this e of tau, this is called as the auxiliary mean. I can rewrite it as e of tau so I have taken e out of this. Okay, and this if we like, we could write it as 1/2 of so we introduce g tau as e square matrix 1 by 1 matrix. Okay, 1 by 1 matrix. So its determinant g tau would be e square of tau, and its square root of the determinant would be just e of tau, and here I can write it as this, and so this is square root of this is just e of tau, and you see here g tau is this, so g tau would be e to the power minus 2. Okay, if I if we take this g tau as e square, then g tau is this to the power minus 1, inverse of. Okay. So this action could then be recovered as e of tau, e of e to the minus 2 of tau x square minus m square. So this is this particular action is called as the Polyakov action for the relativistic point particle. And here E tau is the auxiliary field. Now you can do all the standard manipulations with this. So if you had the action would be d tau times the times you can put this L here. Okay, you can put this L here and you will have the Polyakov action. Now let me recap few important properties of this action. Okay, let me remove this. We can do a few standard things with this action. Like we can vary the action and obtain the equations of motion. There are two fields in the theory, E of tau, x mu of tau. We will obtain two Euler-Lagrange equations. So I don't derive them, but I just write down the I just write down E of tau is x mu dot divided by m. This is E of tau. This is one Euler-Lagrange equation, and the other one is E inverse of tau into x mu of tau equal to 1. Okay, so these are the two equations that you would obtain by the variation of this. And if you start with the action of the theory, Polyakov action, and if you substitute or make use of the Euler-Lagrange equation that you obtained by the variation of the auxiliary field E, what happens is that you recover the Namu-Goto action. Okay, so let me skip the details, and it only implies that the two actions are classically equivalent. Okay, so if you obtain use the action Polyakov action and you substitute one of these equations that is obtained by the variation of E into the action, you recover the let me skip the details. Then you would obtain the the other important point about this action, which is important, that this action has some gauge symmetries. What are these gauge symmetries? These are the word line result from the translation of the in the word line space. Okay, so x mu goes to x mu of tau plus let me call it delta x mu of tau. This delta x mu is equal to xi of tau into x mu of tau, and E of tau goes to E of tau plus delta E of tau, where delta E is the time derivative of xi into E. So these are the diffeomorphism or the word line invariance transformations, word line reparameterization invariance as it is called. So here what is xi? Xi is a parameter which is the gauge parameter. Okay, and there is only one gauge parameter, xi of tau. Okay, and so there is a gauge symmetry in the theory, And you can use this gauge symmetry of the theory to pick some gauge in the theory. And what you can do is, E of tau, you could put equal to 1 or equal to 1 by m. So this for m equal to 0, this for m not equal to 0. Okay, so this is called gauge fixing condition. Okay? Gauge fixing condition. You can fix the gauge in this manner, E of tau. So if the particle is massless, then you can fix E equals to 1. If the gauge particle is massive, then this E of tau is 1 by m. So these are some important points. Let me leave many more details of these two that we did last summer. Okay, but then let us go to its further generalization. So what we are talking right now is the relativistic point particle. We can now talk about the relativistic strings. So what happens is, if I have a point and this point moves in the space-time, it would trace out a curve. Okay, this would trace out a curve. Supposing I move this curve, then I would span a sheet, okay, or a membrane, right? And if I move this membrane upwards or downwards, then I would span